So we're on lesson 4, I think. Yeah. I never know the numbers of the lessons. I get really confused. But so yeah, thank you for putting your Penn State IDs in the I almost called it the Snapchat box. In the chat box. Thank you for that. Okay, so we're going to talk about confidence intervals. I love confidence intervals. They're so fun, and they give us a lot of information. So, but first, it is important that we review samples versus populations just to understand that. So this is just a review basically, and also I know some people were asking about a chart that kind of deviates the different notations we use. So I just want to show you guys this. These are the different symbols and that we use to describe either statistics or populations. So you can see the left hand side for that column is going to be all the ones that we use for sample statistics. So if you see X bar, that's going to be a sample mean. But if you see the mu, that's what the little weird looking mu thing, we call it a mu. I don't know. But if you see that, that's going to be a population mean. This will come into play especially when you're reading different equations and stuff and different questions. You want to make sure you're picking out the right information. You understand where this is all coming from so that you plug in the right numbers for in the equation. So, and that's just a reminder there that our statistics are random and they vary sample to sample. So that's just a reminder down there. So this is just to keep in mind, so you understand the different symbols that we do use in comparison to populations and samples. Just keep in mind too that populations are our overarching group that we take the samples from. So that is just a little review of that. Okay, so sampling distributions, that's basically, this is the basis of where we get that confidence interval from. So first we take that sample from our population, but then basically the distribution, we come out with is going to be our sampling distribution. So it's the distribution of sample proportions with a mean and a standard deviation. So that's just saying that after you take all those samples and then you put them on a curve, it's going to have a mean in the center, and then your standard deviation is your spread. So that's just that's all it is. It's just kind of displaying your samples. Okay, standard error. This is it's also kind of known. It's a standard deviation, but it's specifically a standard deviation of our sampling distribution. So just keep in mind that whenever we're talking about categorical variables, that is talking about proportions. And then anytime we're talking about quantitative variables, we're talking about means. So these are things just to keep in mind that you're never going to have a quantitative variable with a proportion. That just doesn't work. If you think about it, if you have a proportion, it's kind of like one number over the other, obviously. So that's going to be categorical, like the amount of people who said yes over the total amount, something like that. But then for quantitative, your mean is your average. So if you add them all up and divide by a certain number. So remember, quantitative variables have to do with that value. So that's why it would have to do with the mean. So yeah, basically, so the inverse relationship with sample size, all that's saying is that if our standard error goes up, that means we had a smaller sample size. So remember, we always want to have a large sample size no matter what. So if we increase our sample size, we are going to have a smaller standard error, which is good. And then if we do decrease our sample size, we will have a larger standard error. And then also keep in mind, if our sampling distribution is conducted using data from a population, then the mean of the sampling distribution will be approximately equal to that population parameter. So it's just saying the fact that if we have the data from the population and then we have our sampling distribution, they're going to be approximately equal, if it's a representative sample and whatnot. Okay. Yes, confidence intervals. Here we go. Okay, so remember the empirical rule that we talked about before. So that's the whole situation is that you have the 68% of the data between plus or minus 1 standard deviation, 95, and then 99.7. So basically, we're going to like apply that now to find confidence intervals. So we're kind of like using that in real life, if that's what you want to call this. Okay, so when we have, this is just like a basic definition of a confidence interval, okay? So it's a range computed using our sample statistics. Those are the ones we got from our population. And to estimate an unknown population parameter with a given confidence level. And then that's the point estimate plus or minus 2 times the standard error. That's like our basic confidence interval equation, okay? So basically, if we don't know our population parameter and we want to estimate it, the best way to do that is to take a bunch of samples, and then from those samples we will create a sampling distribution, and then we're going to create a confidence interval to estimate where we think that the actual population parameter is. So we make a claim of that we are a certain percent confident that our population parameter is within the range that we get from our sample statistics and that sampling distribution. So kind of to review again, we take a bunch of samples, put them on a distribution, and then we go ahead and compute a confidence interval, which is, I'll show you how to do that over here. And you compute the confidence interval, and then that's going to be predicting something and estimating, given a certain confidence level, where you think that population parameter is. So yeah, this right here, I kind of want it to be written out differently, actually, just so you see it. So we have our point estimate, and then plus or minus 2, then times our standard error. Standard error. Okay. So that's like the equation you use to find your confidence interval. And so just to kind of go over like each part of this, our point estimate is our sample statistic. So that's going to be our center. So remember, p hat is going to be for our categorical variables. That's going to be our center there. And then our x bar is going to be our mean, our center for quantitative variables. So you have your point estimate. So this is the center. And then the whole point of this plus or minus is because we're trying to find a range. So the plus is going to give you the high end of your range, and then the minus is giving you the low end. So that's why we do both of them. And then this 2 comes from the fact that, remember in the empirical rule, TBT to that, how do I draw on here? Okay, empirical rule, we have, oh, I see. Ha. Okay, remember we had this situation with, wow, that is a nice normal curve. Okay, so remember we had this situation here that if we have our mean, being 0, and then this is 2 standard deviations, that this is 95% of our data, if you do recall from the empirical rule. Okay, so 95% of our data lies within plus or minus 2 standard deviations. So this 2 comes from the fact that we are multiplying it by that because we're finding how far out on this on your sampling distribution is 2 standard deviations out. Because if you go out 2 standard deviations from the left and the right, then that's giving you 95% of your data in the center. Because the empirical rule is just like standardizing that. So it's just saying no matter what your standard deviation is, if you go out 2 standard deviations to the left and to the right, you're going to have 95% of your data here in the center. So that's where that comes from. And then your standard error is just going to be either from your proportions or your means, and that's just going to be the standard deviation of those. So yeah, and so I think it's better to understand like where these parts of the equation are coming from. You can plug and chug and just kind of put in the numbers and whatever, but if you don't understand, like why we're multiplying by 2 and why we're using this like sample statistic, why is the point estimate the thing that we're doing plus or minus with, it's not that helpful. So you definitely want to kind of understand these concepts, why we have certain pieces in here that we do. And also keep in mind our multiplier isn't always going to be 2. I'm just saying it's 2 for a 95% confidence interval. But for example, if we want to do you probably wouldn't ever do this because Like it's kind of silly. I jinxed myself by saying the normal curve was negative. You wouldn't really do this because this is just not logical. It's not a high confidence level. But if I was trying to find a 68% confidence level, I would do, my multiplier would technically be 1, so you wouldn't really need it there. But that means, because that's going to be 68% of our data, according to, so this is all coming from the empirical world. So basically, the point being is that our multiplier is going to correspond with whatever percent confidence interval we want. So it's going to be whatever percent is within plus or minus that multiplier. So it's not always going to be 2. We'll learn, there's different like common ones that we use, but it's usually on the higher end. Like I said, you're not going to see like a 68% confidence interval, but that's just an example. Yeah, okay, and also sample size and confidence interval. The whole situation with that is, remember, we want a large sample size, so as that sample size increases, our confidence interval is going to become more narrow. So that makes sense, because if we have a larger sample size, we can be more confident that the population, a parameter, is within a smaller amount. So, it kind of gives us more information there. We're not choosing from a large, really wide confidence interval. We have like center thing. Okay, what is the rule of sample proportions and central limit theorem? Yeah, so basically, let me see. Do I like it? Okay, so those are basically, yeah, good question. So those are basically just the different ways that you would find your standard error. So they sound really like complex, but the rule of sample proportions is just how you find the standard error of proportions, and then central limit theorem is how you find the standard error of means. So it has to do with, I believe we go more in depth into it later in the semester, but yeah, I'm pretty sure we do. It just has to do with, there's certain like things that have to be met before you're able to move forward with your problem. So the rule of sample proportions, for example, it's basically like making sure you have a large enough sample size and everything, and then central limit, same thing with that. They're just making sure that you have all the qualifications in order to move forward with your problem. Because if you don't meet the certain aspects of the rule of sample proportions or central limit theorem, you can't go ahead and continue that. So, but yeah, that's what they are, but that's also where you find your standard error. So does that make sense? Like I said, we'll probably go more in depth into it later on, but just for now, kind of understand that's where you get them from. So good, bad, okay. Oh, I look crazy today. Okay, cool. Alrighty. Mouse. Alrighty, so this is just, why does it do this? Okay. Alright, so Empirical World, this is just, I basically just said all this, so I won't go too far in depth into it, but all this is saying is that, the same thing I just said, that, we get this too from the fact that we are talking about a 95% confidence interval, if we are talking about 95%. So once again, I just showed you plus or minus 2, then 95%. So I will not continue to talk about that. Probably get it by now, and you're like, okay, enough. So we will move on. Okay. All right, so when we interpret this confidence interval, after we go through all that, we take these samples, we make that distribution, we do that equation with the point estimate and the 2 and the standard error and plus or minus all that, we're going to get a confidence interval. So it's like, oh, okay, cool. We have a lower bound and an upper bound. So now it's kind of like, what do we do with that? What does that mean? So if you want to interpret a 95% confidence interval, this is basically, I kind of put this in quotes, like the way that you're always going to kind of come to this conclusion. So we always say we are 95% confident that, and keep in mind, don't get confused, this can be a different confidence interval, but I'm using it as an example because, number one, it's very common that you'll be doing a 95% confidence interval. The multiplier of 2 is very easy to go along with. But like I said, this could be a 90% confidence interval, a 99, it could be any of them, but I'm just discussing for a 95% confidence interval for an example. So we are 95% confident that And then keep in mind, so we're always, hey now, okay, so we're always talking about populations. So I always see people struggle with this. Make sure that you understand when we make this conclusion, when we're interpreting this interval, we're talking about our population, proportion, or mean. Okay, so remember, proportion will be if we were talking about categorical variables, mean for quantitative. So keep in mind that when we make this conclusion, we're talking about the population, okay? If we have the best thing to keep in mind is that when we take these samples, because we're trying to estimate the population proportion, we're trying to find that, or population parameter, that's what we're trying to find. So after we find that sampling distribution and we're interpreting it in terms of what we found out about the population, okay, what we think the population is. So remember I talked about this cycle thing. So we have, no, just kidding, undo. Okay, so we have our population, and then we have our sample. Okay, so in this case, so remember, we take samples from our population, and then I talked about, remember, and then we use that to make an inference. We use the sample to make an inference. You probably can't read that, I'm sorry. To make an inference about our population. So we are 95% confident that the population proportion or mean in question is between, and then whatever your confidence interval that you got is. So for example, like you're going to get two numbers. One's going to be the lower bound, one will be the higher bound. So make sure you do that. You'll see plenty of questions where it says, you know, in like multiple choice, like we are 95% confident that the sample mean is between da-da-da. No, not sample. We're interpreting it in terms of the population. We already did all this stuff with the sample, so now we're taking what we have of the sample to infer about the population. So this is always population mean or population proportion. So keep that in mind. Okay. Hey, let me clear this. Boop, boop. Okay, cool. So bootstrapping. Last semester I had someone ask me where that word came from, and I was just like, I don't know, but it has something to do with it's like something in history that like they would like continue to do something with, like, it has to do with boots. I don't remember, but it has something to do with that. There is a meaning to it, but you don't have to worry about that. But some people ask me, and I'm just like, So I was like, criteria and statistics, not vocabulary. But okay, so bootstrapping. This is what we use if we want to construct a sampling distribution, but we don't know the population parameters. Okay, so it's the same situation where we like do like a sampling distribution. We're making an inference about the population, but in this case, so this is the definition: a procedure that uses data from one sample to generate a sampling distribution. So this is often used if we don't have a big enough sample to like just take from and then take more from and take more from as your samples. In this case, you're going to have your sample, take something out of it, but then you have to put it back. So like, for example, if you had a jar of, 10 marbles and you want to take samples of it, and you want to take samples of 2. So you take 2 marbles out, that's your sample, analyze. Instead of going ahead and just taking another 2 out of the remaining 8, you got to put those other 2 back in. So you're always going to have the same sample size every time because it's with replacement. So yeah, and the bootstrap distribution is just like a sampling distribution. It's just all your bootstrapped values and then put on a distribution. So. Okay, so these are just different, these are 2 different bootstrapping methods when we have a 95% confidence interval. There's 2 different ones. You have your standard error method, and then you also have your percentile method. So these can both be done on StackKey. You just change the setting for either standard error or percentile. The main thing to keep in mind here is that with our standard error method, we do have to have an approximately normal curve. But if it's skewed, you can't be using that. If it's But then percentile method is favored because we can use it no matter what. So we can use it if the sampling distribution is skewed, if it's normal, whatever, you can use that anyway. So yeah, and then remember, a standard deviation of the bootstrap distribution is our standard error that we're going to use to construct that bootstrapping confidence interval. So yeah, that's all. These are just different methods that you could use to find that. So yeah, just to go ahead and highlight on StackKey, like if you were, this is just like screenshots I took as an example. So basically this is just how to like read the different things on StackKey. So if we do a bootstrap method, standard error method, what we're going to get here is, so remember, it has to be approximately normal for this. In the top right hand corner up here, can you guys see my mouse? Just like, I just, like, can you see when I'm like twirling all around like this? Or like, oh, okay. That's so exciting. Okay. Okay, cool. Because like on Blackboard, people couldn't see it, and I'd be like pointing to stuff. I'm like, you see this? And everyone's like, the screen is just the screen. But okay, cool. So up here in our, in the right-hand corner, it's going to give you the amount of samples you took, your mean, and your standard error, okay? So all I'm showing you here is that like your mean is going to be plugged in up here with your, you know, I just color coded it. I like color coding it. I'm visual. So your mean is where you plug in for your point estimate, p hat, your this is your sample statistic of a proportion. Then our standard error is down here, and that's what you're going to plug in there. So that's all I'm really showing you here, is just kind of how to read it. Same thing here if we were talking about a mean. And once again, this is for standard error method. So as you can see, this is approximately normal. And so then your mean here is what you plug into here. So like, I'll just do an example just to make sure this makes sense. So like if I were to go on StackKey and I have all this information, I would go ahead, if I want to construct my interval, I would do 16.006 plus or minus for a 95% confidence interval 2 times my standard error. So that's how you would pull from this information to put it into this equation. So that's all that is. This took me a long time, by the way, to like highlight them in color code, so I hope you enjoy this. But so yeah, okay, and then remember our other method is our percentile method. We can use this if it's skewed, normal, whatever. And the only difference here is that we are able to find our lower and upper bound without doing the equation. We can literally just hit two-tail, and then you get your lower and your upper bound here. So this for a mean. So quantitative variables, as you can see, you know, they're whole numbers, or not whole numbers, they're like actual values, when in comparison to, if we have a proportion, it's going to be between 0 and 1. Remember, proportions as decimals are always going to be between 0 and 1. So here you have our lower bound and our upper bound. So all you do here, and as you can see, this is 95%. So remember what I said, that means that this number here is minus two standard deviations, and then over here is plus 2 standard deviations, and that's why this is 95% of our data. And in StackKey, you can go ahead and click that and change it to whatever you want. But and then here's your mean. So yeah, that's that. Ooh, we're already at review questions. Crazy. Okay, so this is this question is just to kind of review those symbols, make sure you understand the difference there. So which of these statements is true about both P and mu? So go ahead and read through these and let me know what you think, and we'll review it then. Yes. Woohoo. Good job. You guys are doing a great job. Yes, the exclamation points and the slash, Maria, A plus. Just kidding. So good job. Our answer here is definitely B. So just you're fine. You're totally fine. So just if we go through this, just you guys clearly get it, but just quickly to review it. So this says P and mu are both statistics. That's like absolutely wrong because they're both parameters. So burp. So that's why B is actually correct because they are both parameters. C is wrong because it says P is a statistic, mu is a parameter. This is true, but this is not true. So nope. And then for D, P is a parameter, which is true, but then mu is not a statistic. So that's not right either. So our answer is B. Woohoo! Good job, guys. Perfect. Alrighty. Okay. A random sample of 100 preschool children, 70% like carrots. That's nice. Good beta carotene there. Construct a 95% confidence interval for the proportion of all preschool children who like carrots. So I gave you the standard error there, so you don't have to go ahead and calculate that because it's just plugging in the equation. So there's your standard error. Go ahead and try to find this confidence interval and let me know what you get. Okay, let's review this one. So Hannah, A plus, correct answer. So let's walk through this one and see how to do it. Okay, so remember our general formula for all confidence intervals. It's going to be our point estimate, and then plus or minus, and we're talking about a 95% confidence interval, so our multiplier is going to be 2, and then times our standard error. So if we were going to go ahead and plug all of our stuff in, our point estimate here, so this is 70% is our point estimate. That's the percent that like carrots. So if we turn that into a decimal, that's just going to be 0.7 plus or minus 2 times our standard error, which I just gave you down here. So 0.046. Boop. And then if we were to solve this, we would go ahead and get, like Hannah said, 0.608. If I could, okay, unfortunate. I need to be able to draw. 608. comma 0.792. So that is how we find it, and that is going to be our 95% confidence interval. Does that make sense to everybody? Woohoo. Cool. Where did I forget parentheses? Where? Okay. Okay, yeah. It's probably because I'm scribbling all over this. Here. There we go. You can also write, I mean, you could say it without parentheses too if you're, just writing it out, but they're usually used so that you can understand that's like the range that we're going in between. But, so yeah. Okay, cool. All right, what do we got here? Okay. Okay, which of the following is true about the population mean and the sample mean? So this is kind of reviewing about the different characteristics of populations and samples. So go ahead and try these ones out. Woo, woo. Okay, great job. Yeah, absolutely. So let's go through all of these. So our answer is D. So great job. So let's go through these. So A says values of the population mean will vary. No. So it's already wrong. Population, remember, is fixed, so that doesn't vary. And this says the sample won't, but that's also false. Not true. B, values of both population and sample mean will vary. Once again, population mean does not vary. So, oops. So B is not correct. And then C, once again, says values of population mean will vary. No, they won't. That's not how we do things. And yeah, so that's not right. And then so yeah, D is our correct answer then, because sample mean are going to vary, and then that's it just kind of, that's it. So that's the correct answer. So yeah, our answer is D there. So great job, guys. Alrighty. Okay, so it's just a quick question. So we have data from a sample of 10 stat 200 students. You and 9 of your classmates. So if we were to take a bootstrap sample, is it possible that you could be selected more than once? Tammy is thinking quick. Yes. I mean, yeah. I honestly was thinking that in my head. I was thinking yes, and I was like, I don't want to be weird. Well, you guys already know that I'm weird, so. But good job. You guys are absolutely correct. So this is correct because remember bootstraps, you're able to draw with a replacement. So the same individual can be selected more than once. So yeah, we're down with the kids and their lingo. I'm 21. I'm not really sure why I'm saying that, but good job, guys. That is correcto. All right, true or false question. If a bootstrap distribution is approximately normal, the empirical rule can be applied to construct a 95% confidence interval by multiplying the standard error by 2 to get the margin of error. So go ahead and think about this one. Yay, okay, good job. So yeah, this is definitely true because basically what this is the definition of the standard error method for bootstrapping. So remember, our standard error is when we utilize that point estimate. I'm going to write this a million times. Plus or minus 2 times our standard error. Okay, so yeah, that's all that is basically the definition of that. And then keep in mind that this right side of your equation is also known as the margin. Margin. What did I just do? It's supposed to be of SOS. Okay, here we go. Of error. So yeah, just keep that in mind. Your multiplier times your standard error is your margin of error. So that's your right side of your equation there. So yeah, that's a standard error method. So good job. Okay, so I think I have a few more. Oh, more than a few more. We have like 4 left. So much practice today. Okay, so StackKey was used to construct a bootstrap sampling distribution for the mean Atlanta commute time. A total of 5,000 bootstrap samples were drawn from the available samples of n equals 500 commute times. This bootstrap distribution has a mean of 29.099 and a standard error of 0.930. Using the standard error method, what is the 95% confidence interval for the population proportion? So utilize this distribution that I gave you here on the left. Let me know if you can't read any of that. I know it's a little smushed. But go ahead and try to find this 95% confidence interval with what you have here. All right, great job. Good job, Hannah. That is absolutely correct. So I don't really have room to write. Oh, I forgot I can write like up here. Oh, oops, I put up that. Okay, so let's go ahead and look at this. So I always, like I've told you before, I like to kind of write out what we have. So we have that our mean, remember, is going to be our x bar, and then that's going to be our point estimate. And then in this case, that is the 29.099. And then we have our standard error at 0.930. And since it's a 95% confidence interval, our multiplier is going to be 2. So utilizing all that information, we can go ahead and plug that into our equation. So remember, point estimate plus or minus 2 times our standard error. So if we go ahead and plug all that in, we have 29.099 plus or minus 2 times 0.930. And then if you do that equation, you're going to end up getting a confidence interval of 27.239, comma 30.959. Boop. Cool. So that's our final answer down here. Does that make sense to everyone how I went through that process? Yes, no, maybe, don't care. Oh, okay, yeah. Yeah. That's sometimes I lose a chat box too, and like and I'll be like, are people talking? Actually, last semester, like I made a habit, not intentionally, but I would forget to like unmute my mic, so I'd just be talking along, and everyone's like, "Hello." I was just like, "Sorry." So, but yeah, okay, good. Yeah, make sure you just read. That's the main thing. With statistics is to make sure you read all the parts of the question, because one change in a word can change the whole situation how you're gonna do it. So, but yeah, all right, cool, clear. All right. Let's see. Okay, here's another one. So data from a representative sample of 507 adults who exercise regularly were used to bootstrap a 95% confidence interval of the mean wrist diameter in centimeters in the population of all adults who exercise regularly. So I gave you a Minitab Express output here on the right. So go ahead and interpret the confidence interval. So you already have it. I already gave you the confidence interval down there. So go ahead and interpret this. So remember, as a hint, we are 95%. Da-na-na. Okay, so go ahead and come up with an interpretation for this, and then we'll go over it. Yes, those are the numbers. Let me write them. Let me write them up here. So the confidence interval that you're given is 10.4602 and then 10.6217. All right, so yeah, go ahead and interpret this. In this case. Whoop, whoop. Okay, good. So yeah, let's go ahead and go through this. So remember, where's my little pen? Okay. So yeah, great job. So remember, we always start out with, and we're talking about 95% still, so we are Penn State. Just kidding. Actually, funny story about that. I tutored someone before, and we kept going over these because they were really struggling with it. And they asked, they're like, do we keep going over this because Penn State's trying to like make us keep saying we are, and that's why we keep like saying this for the confidence interval interpretations. I'm like, no, that's not. People at other schools do confidence interval interpretations too, but now every time I hear it, I just like hear the Penn State chant. It's bad. But so we start this out. We are 95% confident that, and this is where it gets crazy. So remember, we want to talk about whatever variable so are we talking about means or proportions? That's what we have to decide. So you can say, so in this case, we're talking about means. So we say the mean, and then the mean what? So what are we looking at here? We're talking about wrist diameter, because that's clearly interesting. But the mean wrist diameter in the population, wow, I can't talk and write at the same time. In the population there we go, of, and then we want to find what was our population that we took it from. So right here, population of all adults who exercise regularly. All adults who, and then exercise regularly, is between 0 or 10.462 to 10.6217. So, in conclusion, we are 95% confident that the mean wrist diameter, that's our variable, in the population of, who is our population, all adults who exercise regularly, is between, and then the lower and upper bound of our confidence interval. Does that make sense, everybody? Yay. Woo woo. All right. Ooh, I have a follow-up question. We ain't done yet. All right, oops. Okay. Okay, so this is the same thing, same many-tab output. But given this, is there evidence that the population mean is different from 11 centimeters? So think about this one, given what we just concluded with that interpretation and all the information you have here, and then let me know what you think. Okay, so let us think about this. So we figured out, so our confidence interval is, once again, because it's so small, 10.4602, and then comma, 10.6217. Okay, so it's asking, do we think that we have evidence that the mean is different from 11 centimeters? Okay, so in this case, we're saying that we are 95% confident that that population mean is within these two numbers. So we are very confident, like 95%. That's a high confidence level. We're 95% confident that our population mean is within this. So anything outside of this, we're only 5% confident that it's out there. We're only that's our error. We're 5% confident that the population mean is out there. So we're more confident that it's in here. So it's saying, is it different from 11 centimeters? So 11 centimeters is going to be out here. Okay. So this is we're not confident that's out here. So it's saying, is there evidence that the population mean is different from 11? Well, yeah, because 11 is not contained within this 95% confident interval. So we can't include it in the fact that we're 95% confident that it could be 11, because it can't. Well, I mean, it can be, but we're not confident that it is. So this answer would actually be yes. We do have evidence because all the numbers in here are different from 11. They don't include 11. So we do think that the population mean is different. Does that make sense how I explained it? Why sigh? Is that this is why we do these, because it's better if you get them wrong and then learn. I don't know. I would always learn better from the questions I would get wrong, so oh yeah, don't go all crazy. This is just but yeah, okay. I'm glad you guys understand it. Cool. Okay. All right, one more. Thanks for hanging in, guys. Okay, so last but not least, one more interpretation. And most of the time I'm guessing. Yeah, I know. You always just want to make sure that, you're answering to the best of your ability, and then, don't tell me you understand it if you don't, because I'm more than happy to go over it again. So, it'll only make you learn more. So, but yeah, okay, so go ahead and try to interpret this confidence interval. So our last one. So remember, we are 95%. Go ahead and check this one out. Okay, let's go over this one. So remember that we always start out, I'm picking a new color. I'm sick of this yellow. Okay, so we always start out, we are 95% confident that, and now is when we put in what population we're looking at. So are we looking at a population mean or proportion? And up here, we see it says proportion. Also, you can tell because these are between 0 and 1, so that makes sense. So that the population and then proportion is between, and then our two numbers, 0.200 and 0.533. So, you know, we don't have like a specific like variable that was going on here, so we could just say population proportion because we do know that much. So yeah, that is how we would interpret it. Does that make sense to everybody? Yay! All right, cool. All right, that's what we got for today. So you can go ahead on my YouTube channel and watch these back and all the other ones from the other weeks. Our next review will be on Sunday, same time, same place, 10 o'clock. And it's already September. Oh my goodness, it's halfway through September. So yeah, I think everyone gave me their email, which is good. If you have any more questions for me, let me know. If not, that's what we got for tonight. Thanks for hanging in. I know that's a long lesson. So okay, yeah, wait, I am interested. I want to see this. Okay, what is bootstrapping? Does it say anything about boots? I swear to God. Okay. Yes, see, it was okay. See, okay, I knew I wasn't going crazy. Something I was gonna say, I was like, if I swear to God, if it was okay, yeah. That's funny. I'm glad you showed me that. See, you learn something new every day. Curious minds, that's how you grow. So cool. But yeah, okay, cool. So yeah, let me know if you have any more questions. You're probably pooped by now. Enough statistics. I will try. Thank you, Maria. Yeah, I will definitely. I know I need some tea or something. I'm just like, I don't think I sniffled that much, though. I think we're okay.